Welcome to the Professor's Du Bois channel. This is Professor Victoria and Professor Corey, and today we're going to be talking about oxidation reduction reactions.
Okay, so oxidation reduction reactions are sometimes called redox reactions, and they're kind of unique because we talked about acid-base reactions before where there was a transfer of a proton. Well, redox reactions involve the transfer of electrons, and this is just a little different. So most of our combination, decomposition, and single replacement reactions are redox reactions.
Oxidation reduction reactions, they always occur together. Like there's an oxidation piece and a reduction piece, and it can't happen alone because if something loses electrons, something else has to gain the electrons. The electrons don't just disappear. So when we're talking about redox reactions, we're talking about both. So oxidation is the loss of electrons. So the species that loses electrons is oxidized, and the species that gains electrons is reduced. And we learn this or kind of remember it from just say Leo says grr. So Leo the lion says grr, lose electrons, oxidation, that's Leo, and gaining electrons is reduction.
Good tip.
Good tip, pro tip.
So here's an example of a reaction. It's written in words, and below we have the balanced equation. So we have zinc metal placed in a copper nitrate solution. So that's aqueous, aqueous solution. And then we form copper on the zinc. So if we look at this reaction, we have the zinc solid with the aqueous copper nitrate going to zinc nitrate and copper. So it'll be nice to kind of clean this up by making a net ionic equation. We know how to do that. So we're going to separate, we're going to break apart soluble ionic compounds and strong acids, and we've got a couple compounds here, and after we cross off our spectators, we have the net ionic equation below. And you can see from this equation that zinc, just solid zinc, went to the ion. So it lost 2 electrons and ended up with a +2 charge over there as an ion. And our copper that has a +2 charge on the reactant side goes to copper solid. So it must have gained 2 electrons. This is a redox reaction.
So the electron acceptor, again, is reduced, right? But we call it the oxidizing agent. So it's the agent of change. Whatever that agent does, it does to something else. So if it's the oxidizing reagent or the oxidizing agent, then it itself is reduced. So sorry about that. We didn't make up the rules. It is a little bit confusing, but the reducing agent donates the electrons to the species that is reduced and is therefore itself oxidized.
Well, let's try to clean that up a little bit with an example. So if we go back to our zinc and our copper nitrate example, when we look at this, zinc went from the solid and ended up being a cation, 2+. So it must have lost 2 electrons. Because it loses electrons, it's oxidized. Because it's oxidized, it's the reducing agent.
Right.
And if we look at our copper ion, the copper 2+ is a reactant going to the solid copper. We can see that it gained 2 electrons. So gain electrons, that's reduction. And because it's reduced, it's considered to be the oxidizing agent. It's really not that bad.
So you have to really think about the fact that the electrons are an entity. It's something, and it has a negative charge. So you think of losing something, you think of getting less, but it really you're losing negative, so you're becoming more positive. Can we go back one?
Sure.
I'd like to show how this 0 here, it's a neutral, right? So it's solid, and it's getting more positive. So it's losing negatives and it's retaining its positives.
Right.
And so it gets a higher number on a number line by losing negatives, and it's a little bit confusing.
So the solid zinc has the same number of protons and electrons, and the ion with a 2+ charge has lost 2 electrons.
Right. Just like when you're forming your ions, you can kind of think of it that way. We often will split these equations into half reactions. So we split the oxidation and the reduction apart so that we can see that transfer of electrons. Who's gaining the electrons, who's losing the electrons, and we split them into what we call half reactions. So we have half, sorry about that. Half reaction only shows the species involved in the oxidation and reduction, first of all. So if there's other species that have not gained or lost any electrons, we don't put them in the half reactions.
Kind of like spectators.
Yeah, kind of like spectators. And when you add them, they make the net ionic equation, which is kind of helpful.
Yeah, and that's a lot in one slide. Let's look at an example. It'll make more sense.
It's always better.
Yeah. So let's go back to our zinc and our copper nitrate solution. So if we wanted to write half reactions, we know that the zinc lost 2 electrons and formed the zinc ion, the 2+ ion. So the half reaction for that, for the loss of electrons, would be the solid zinc going to the ion, aqueous solution, plus 2 electrons. Now, what's a little bit weird here is what you want to do is you want to write zinc solid minus 2 electrons goes to the ion. And we didn't really lose electrons at all. They were transferred to that ion. So really the solid is on the left and the ion and the electrons are on the right.
Yeah, and when you're looking at chemical equations, you never have something minus something. It's not a math problem. It's the electrons are an entity. So if they came off of the zinc, now we have them separate. So we have an ion and the electrons, they just happen to go somewhere else. They went to the copper ion.
The reduction half reaction makes a lot more sense because you write the ion, in this case the copper ion. It's not always going to be an ion, but in this case we've got the copper ion. We say the copper ion gains 2 electrons or plus 2 electrons and forms the solid. Those are a little easier to write. So we talked about adding these 2 reactions together and producing the net ionic equation, and the way we do that is we just simply combine the elements or ions on the left of the arrow for both reactions and the same thing on the other side. Now our electrons have to cancel out. They have to be the same. So if this example, if our copper said +1 electron, we would have to multiply everything by 2. We'd have 2 copper ions and 2 copper solids. But in this case, we have 2 electrons on the product side, 2 electrons on the reactant side. Just like spectator ions, we can cross them out. So our net ionic equation is going to be zinc solid plus the copper 2+ ion. You gonna write this down?
It's up here.
Oh, it is up there. And it's going to form the zinc 2+ ion in the copper solid.
Yeah, and this is a very simplistic example. If you may or may not have it equal, add up to the net ionic equation if you get into very complex reactions where not everything is involved. So sometimes you have some species that are not involved in the redox, the gaining or the losing of the electrons. So we're just starting simple here. We'll get more and more complex as we go.
We're making it easy.
Yeah, that's right. So here's some practice. We want you to take a look at this, determine what has been oxidized and what has been reduced. Remember that your pure elements are starting out with an oxidation state of 0, and you can break them apart into the half reactions, and you can look at that. But we want to know what is oxidized and what's reduced.
And I think a good thing to add here is that it's going to be the reactants, and we didn't say that. And
that's right.
It's a good point. Is whenever you're looking for something that's oxidized or reduced, it's going to be on the reactant side of the reaction.
Right. It'll be one or the other of your reactants. Pause the video and give it a try.
Okay, so here are your answers. Hopefully that is correct.
Yeah. I want to add here, so when something is oxidized, remember that's the reducing agent. Just to be confusing.
It's not that bad. It's not that bad.
And then the oxidizing agent then would be down there.
For sure.
Yep. So this is the way that we've shown you so far. This is very easy to see the flow of electrons in this example and examples like the ones that we gave you to practice. But in many cases, it is more difficult. So we want you to stick around, come back to the next video in this series so that you can determine how to approach these problems when it's a little bit more complex.
All right. Stay tuned for that.
Thanks for watching.
Bye.
Bye-bye.